There is air around us, and there are rivers and seas near us. The flow of a river never ceases to go past. Nevertheless, it is not the same water as before. Bubbles floating along on the stagnant water now vanish and then develop, but have never remained. Stated in the 13th century, essayist Keima of Japan. In this way, the air and the water of rivers and seas are always moving, as we can see here. Such a movement of gas or liquid, collectively called fluid, is called the flow, and the study of this is fluid mechanics. While the flow of the air and the water of rivers and seas are flows of our concern, so also are the flows of water, sewage, and gas and pipes in irrigation canals and around rockets, aircrafts, express trains, automobiles, and boats. And so too is the resistance which acts on such flows. So let's start and dig a little bit and speak about the beginning of fluid mechanics. The science of flow has been classified into hydraulics, which developed from experimental studies, and hydrodynamics, which developed throughout theoretical studies. In recent years, however, both have emerged into the single discipline called fluid mechanics. Prehistoric relics of irrigation canals were discovered in Egypt and Mesopotamia, and it has been confirmed that canals had been constructed more than 4,000 years BC. Water in cities is said to have begun in Jerusalem, where a reservoir to store water and masonry channel to guide the water were constructed. Water canals were also constructed in Greece and other places. Above all, however, it was the Romans who constructed channels throughout the Roman Empire. Even today, the remains are still visible in many places in Europe. The quantity of water a day used by a citizen in those days is said to be approximately 180 liters. Today, the amount of water used per capita per day in an average household is said to be approximately 240 liters. Therefore, even about 2000 years ago, a considerably high level of cultural life occurred. Before proceeding to describe the development of hydraulics, the Renaissance period of Leonardo da Vinci in particular should be recalled. Popularly, he is well known as a splendid artist, but is also an excellent scientist too. He was so well versed in the laws of natural science that he stated that a body tries to drop down onto the earth through the shortest path, and also that a body gives air the same force as the Renaissance which air gives the body. These testaments preceded Newton's law of gravity and motion, which is the law of action and reaction. Particularly interesting in the history of hydraulics is Leonardo's note, where a vast description is made of the movement of water eddies, water waves, falling water, the destructive force of water, floating bodies, efflux, and the flow in a tube conduit to hydraulic machinery. Leonardo was the first to find the least resistive streamlined shape. Indeed, Leonardo was a great pioneer who opened up the field of hydraulics. Excellent researchers followed in his footsteps, and hydraulics progressed greatly from the 17th to the 20th century. Now we're going to be speaking about hydrodynamics particularly. On the other hand, the advent of hydrodynamics, which tackles fluid movement both mathematically and theoretically, was considered later than that of hydraulics. Its foundations were laid in the 18th century. Complete theoretical equations for the flow of non-viscous, non-frictional fluid were derived by Euler and other researchers. Thereby, various flows were mathematically describable. Nevertheless, the computation according to these theories of the force acting on a body or the state of the flow resulted in a very different outcome from the experimentally observed results. In the 19th century, however, it made such progress complete fully with hydraulics. One example of such progress was the derivation of the equation for the movement of a viscous fluid by Navier and Stokes. Meanwhile, however, in 1869, an important paper was published which connected hydraulics and hydrodynamics. This was the report to which Kirchhoff, a German physicist, computed the coefficient of contraction for the jet from a two-dimensional orifice. The value coincided very closely with the experimental value for the case of an actual orifice 0.60. Furthermore, in the present age, with the progress in electronic computers and the development of various numerical techniques in hydrodynamics, it is now possible to obtain numerical solution of the Navier-Stokes equation. Thus, the barrier between hydraulics and hydrodynamics has now been completely removed, and the field is probably on the eve of a big leap into the new age. Now comes the most interesting part of our lecture, the characteristics of fluids. Fluids are generally divided into two things, liquids and gases. A liquid is hot to compress, and a gas, as in the ancient saying, water takes the shape of a vessel containing it. It changes its shape according to the shape of its container with an upper free surface. Gas, on the other hand, is easy to compress and fully expands to fill its container. There is thus no free surface. Consequently, an important characteristic of a fluid from the viewpoint of fluid mechanics is its compressibility. Another important characteristic is its viscosity. I'm going to speak about the equations later on for both. Whereas a solid shows its elasticity in tension, compression, or shearing stress. A fluid does so only for compression. In other words, a fluid increases its pressure against compression, trying to retain its original volume. This characteristic is called compressibility. Furthermore, a fluid shows resistance whenever two layers slide over each other. The characteristic is called viscosity. In general, liquids are called incompressible fluids, but gases are compressible fluids. Nevertheless, for liquids, compressibility must be taken into account whenever they are highly pressurized, and for gases, compressibility may be disregarded whenever the change in pressure is small. Meanwhile, a non existent assumed fluid without either viscosity or compressibility is called an ideal fluid or a perfect fluid. A fluid with compressibility but without viscosity is occasionally discriminated and called a perfect fluid too. Furthermore, a gas subjected to Boyle's-Charles law is called a perfect or an ideal gas. Now I'm going to be speaking about the units and dimensions. All physical quantities are given by a few fundamental quantities or their combinations. The units of such fundamental quantities are called base units. Combination of them are called derived units. The system in which the length, mass, and time are adopted as the basic quantities and from which the units of other quantities are derived are called the absolute system of units. Absolute system of units, we basically have three main types of absolute systems. We have an MKS system of units, CGS system of units, and SI system of units, which stands for Système International. The MKS system of units is the system of units where the meter is used for the length, kilogram for the unit of the mass, and seconds for the unit of time as the base unit. CGS system of units is a system of units where centimeters is used for the length, gram G for mass, and second S for the time as the base units. System International unit system, it's an international system which is developed from the MKS system of units. It is a consistent and reasonable system of units which makes it a rule to adopt only one unit for each of the various quantities used in such fields of science, education, and industry. There basically I use the SI units in all of the dimensions and the units of my physical quantities. There are 7 fundamental SI units, namely meter, length, kilogram, mass, second for time, ampere for electric current, Kelvin for the thermodynamic temperature, mole for the mass quantity, candela for intensity of light. Those are stated here in this table, as you can see. Now I'm going to be speaking about the equations and in details regarding density, specific gravity, and specific volume. Density is the mass per unit volume is called density, which is generally expressed by the symbol ρ. This is how it's actually shows. So it's actually equal to mass over volume. The unit for mass is in kilogram, volume is a meter cubed. The density of water is at 4 degrees and 1 atmospheric temperature is equal to 101,325 pascals. The standard atmospheric pressure is 1000 kilogram per meter cubed. The ratio of the density of a material to the density of the water is called specific gravity, which is shown right here. So density of the material divided by the density of the water. While the specific weight, it is the weight per unit volume of a material is measured in Newton per meter cubed. So this is how the specific weight equation looks like, which is density times the G, which is gravity. The reciprocal of density is called the specific volume, which is generally expressed as here 1 over the rho, which is measured in meter cubed per kilograms. Now I'm going to be speaking about viscosity, surface tension, and compressibility. Alright, so for viscosity, suppose that a liquid here fills the space between two parallel plates of an area A, each, and the gap is basically H. The lower plate is fixed and the force F is needed to move the upper plate in parallel at velocity U. Whenever UH over V is less than 1500, laminar flow is maintained and a linear velocity distribution as shown in here is obtained. So you can see here we have linear lines. Such a parallel flow of a uniform velocity gradient is called Couette's flow. In this case, the force per unit area necessary for moving the plate, the shearing stress is proportional to U and inversely proportional to H. Using a proportional constant P, it can be expressed as this formula right here. Proportional constant minimum U is called the viscosity right here. The coefficient of viscosity, however, the velocity distribution in the case where the fluid is shown right here in this figure, extending this equation to such a flow that the shear stress Z on the section dy distance y from the solid wall is given by this following equation. The relationship was founded by Newton through experiment and is called Newton's law of viscosity. In university lectures, we can rewrite this equation into this form, which is U is equal to minus the shear stress dN over du. If a fluid with viscosity of 1 pas is placed between two plates and one plate is pushed sideways with a shear stress of 1 Pascal, it moves a distance equal to the thickness of the layer between the two plates in 1 second, as I have explained here. And we can say that the shear stress is equal to T over my area. In the case of gases, increased temperature makes the molecular movement more vigorous and increases molecular mixing so that the viscosity increases. In the case of a liquid, as its temperature increases, molecules separate from each other, decreasing the attraction between them, and so the viscosity decreases. The relationship between temperature and viscosity is thus reversed for a gas and for a liquid. This figure shows how the relationship between the change with temperature of the viscosity of air and water. The units of viscosity are Pascal seconds in SI units and G per centimeter S in CGS, absolute system of units. And Lg per centimeter S in the absolute system of units is called 1. The value V obtained by dividing viscosity by the density, ρ, is called the kinematic viscosity. For water, oil, or air, the shearing stress Z is proportional to the velocity gradient du over dy. Such fluids are called Newtonian fluids. On the other hand, liquid, which is not subject to Newton's law of viscosity, such as a liquid pulp, a higher molecular weight solution, or asphalt, is called a non-Newtonian fluid. These fluids are further classified as shown here by the relationship between the shearing stress and the velocity gradient. A rheological diagram which shows the relationship between the shearing stress and the velocity gradient, and rheology is basically the science aligned to the deformation and the flow of a substance. Now I'm going to be speaking about surface tension and compressibility. Surface tension, it is indicated by sigma newtons per meter minus 1. It is a property of the surface of a liquid that causes it to behave as an elastic sheet, which is force per unit length. Compressibility is shown in this figure right here. So assume that the fluid of the volume V at pressure P decreases its volume by delta V right here due to the further increase in pressure by delta P. In this case, since the cubic dilation of the fluid is V over V and the bulk modulus K is expressed by this equation right here, change of P divided by the change of delta volume over the volume, It is expressed by the derivative dP over dV. Its reciprocal B is called compressibility, whose value directly indicates how compressible the fluid is. So beta over 1 over the previous equation that I mentioned is called compressibility. In other words, we can rewrite this formula as the following, which is the coefficient of volume compressibility K. So in some lectures, they do not get you the previous derivation that I mentioned. They just write you that compressibility is equal to minus 1 over V times dV over dP, which is a measure to the relative volume change of a fluid as a response to a pressure. All right? And this equation is Hooke's law. I'm sure that all of you know Hooke's law from your physics classes, which is equal to this equation right here, Vz1 minus K, which is coefficient of volume of compressibility times the change of the pressure. The reciprocal is the module of volume elasticity K, which is equal to 1 over this, the coefficient of volume compressibility, all right? Now I'm going to be speaking about the coefficient of volume expansion. Thermal expansion is a tendency of the matter to change in volume in response to a change in temperature, which is indicated in this equation right here. And it shows that V is equal to V0, 1 plus the beta times the change of temperature. Characteristics of a perfect gas. Let P be the pressure of a gas, U V the specific volume, T the absolute temperature, and R the gas, the constant gas. Then the following equation results from Boyle-Charles law, which is PV is equal to R times T. This equation is called the equation of the state of the gas. A gas subject to an equation previously is called a perfect gas or an ideal gas. Strictly speaking, all real gases are non-perfect gases. However, any gas at considerably higher temperature than its liquefied temperature may be regarded as approximated to a perfect gas. This shows the state change of a perfect gas. So here we have pressure versus the specific volume. The change in the state of a perfect gas is expressed by the following equation, where PV to the power of n is constant, where n is called the polytropic exponent, as this value changes from 0 to infinity, as shown here in this figure right here. The state of the gas makes 5 kinds of changes, known as isobaric, isothermal, polytropic, adiabatic, and isochoric changes. Those are all the changes of the gas. Now let's move on to our problem. So a pipeline is examined by pressure test at which the pressure reached the value of this value, pascals. The pressure was in a pipeline of this length with a diameter 250 millimeters at the beginning of the pressure test, at which the temperature was 5 degrees Celsius. Determine the pressure at the end of the test when the temperature of the water was 15 degrees. Neglect the deformation of pipe walls, coefficient of thermal expansion of water at the temperature 10 degrees. Consider the value of 1.4 times 10 to the power of 5 degrees Celsius. The model of volume elasticity of water is equal to 2 times 10 to the power of 9 pascals. So you will evaluate all of these values with your parameter of x. Let's say your x is equal to 1 or 2, and then you will get these values. All of the rest are all given values. You would like to know the pressure at the end of the test of the pipe. So we can draw the pipe right here. We can say that this is a diameter, this is the length. We know that at the temperature 1, V, the initial volume, would be equal to the volume at the beginning times T, which is equal to the volume at the end of the P, which is equal to V. So we know that the T2 would be equal to the volume at the end of the test, which is equal to the beginning volume times the pressure, which is equal to V times the P1. So we know that the change of P2 is equal to P2 minus P1, and delta T is equal to T2 minus T1. So the volume at the end of the pipe is equal to the volume at the beginning of the pipe, open brackets, 1 minus capillary times the change of pressure. And we know that the volume at the end of the test is equal to the volume at the beginning of the test, 1 minus beta times the change of T. Those are our equations that we stated previously. all right, for the thermal expansion right here, if you remember. So proceeding, now we know that the volume at the end of the test is equal to the volume at the beginning of the test, 1 minus beta times the change of the temperature. So, and we know that the volume at the beginning of the test is equal to the volume at the end of the test, 1 minus the capillary times the change of P. So if we substitute this equation right here at the volume at the end of the test, we will have that the volume at the beginning of the test, we put this equation right here, V beginning of the test, 1 minus beta times change of T, open brackets, 1 minus capillary times the change of P. These two will cancel each other out. We put this side of this equation on the other side. So we'll have 1 over 1 plus beta change of T is equal to 1 minus capillary times the change of P. And we know that the modular of volume elasticity is equal to 1 over the capillary. So if we substitute this part right here to 1 over the modular of volume elasticity, which is the same thing. So we will have that we will rearrange this equation as 1 over the modular of volume elasticity, open brackets, the P2 minus P1 is equal to 1 minus this part of the equation, 1 over 1 plus the beta times the change of T. Now, you can rearrange this to have the P2, the subject of this equation. So we'll have P2 is equal to 1 minus 1 over 1 plus beta times the change of T times the K right here, plus, because here we have a minus, the other side will be plus P1. So P2 is equal to 1 minus 1 over, now we can substitute all of the values that we have already given, times this value plus the pressure 1 value, and you will have equal to, which is equal to 590960.81 pascals. So I calculated the pressure at the end of the test when the temperature is 15 degrees, which is going to be equal to 591 kilopascals.